Okay, so welcome to the third seminar about open quantum systems and the Lindblad master equation. So in the first seminar, we derived the Redfield equation, that is a master equation, but it is not Markovian. It is Markovian, but it's not completely positive. And in the second seminar, we derived the Lindblad master equation that after further approximations, including the rotating wave approximation, we get to a master equation that is both Markovian, trace preserving, and completely positive. Okay, so at the end of the last seminar, we end up with this kind of equation. Today, what we are going to do is to work an example that you can find also in this paper from myself. Okay. So if you want to, because I won't make the plots and so on, so you can check them, but it will be work with a little more detail than it is in the paper, okay? So basically we end up with this equation, as we say in the last seminar. This equation basically has two parts, so it describes the time evolution of a density matrix. It has two parts. This part that corresponds to the von Neumann equation is what we call the coherent part. Okay, and then we have this other part, that is what is usually called dissipation. So basically this is the one that comes from the intrinsic quantum dynamics of the system, and this comes from the interaction with the environment. Okay, so when I first saw this equation, I understood the derivation, but when I stop here, I say, okay, and now how can we solve it? Is it easy? And mostly, how can I program a computer in order to do it automatically, okay, or autonomously? So this is what I want to do. So let's work on an example. This is what I think is the most simple example that we can work, at least for sure, regarding dimension, because it is going to be the smallest system we can work in quantum physics, that is a two-level system. And regarding the dissipation, it's also pretty easy because we are going to work only with one channel. So here we have many possible jump operators, or many possible channels of interaction between the system and the environment. Okay, we are going to fix that there is only one, okay, and not a very complicated one. So the example basically is a two-level system with dissipation. Okay. Or with decay. So basically our system is the following. We have two levels, okay? It can be a two-level atom, it can be a spin. There are many things. So let's say that this is our 0 state and this is our 1 state. Okay? To make it non-totally trivial, well, first, to describe the dynamics of our system, we have to write the Hamiltonian. Okay? Hamiltonian, first of all, it will correspond to the energies of these two levels. We will set the energy of 0 at 0. We don't lose any generality doing that. And we will call the energy of the level 1 as epsilon. Okay? So any value. To make it non so trivial, we will add some driving between these two levels, so we can have some Rabi oscillation between the levels. This will be given by a term like this: 0, 1 plus 1, 0. Okay, so this is our Hamiltonian. Okay, I said this was the simplest model. No, it could be even simpler if you don't have any driving, for instance. Okay, it would be just a static two-level system, but this is, in my opinion, too simple, and then we don't learn anything about the dynamics, okay? So solving this is a classical problem in basic quantum theory courses, but what we are going to add is the possibility of having also the decay. So you have this Rabi oscillation, but also because of the interaction with the environment, spontaneously, level 1 can transform into level 0. You can see it as, for instance, if it is an atom that can be excited or not excited, the emission of a photon to the environment. Okay? as this photon is not part of the quantum system we are dealing with, that is the atom, we model it out of the Hamiltonian. So we model it with the jump operators. Okay, so this will be our channel. So we will have only one Lindblad operator. It will be just sigma minus, or let's write in the same notation. Okay, let's be consistent. Basically, it will be certain rate gamma that drives the transform 1 into 0. Okay, let's write this in a matrix way. This will be 0, this will be epsilon, this will be j, this will be j. Okay, so basically 0 energy, epsilon energy, and the j interaction between the 0 and 1. Okay, this in a matrix form will be, let's include the square root of gamma. So make it bigger. 0, 0, and then what we have here is that we can take 1 and transform it into 0. So it should be the root of gamma here. We are going to start multiplying now matrices and matrices, so please, if I make any mistake, you would tell me. But this is clear that if you have here 0, 1, transform, and you get the 1 you transform into 0. Okay? Another matrix that we are going to use, because here we have Li, well, L dagger will be just 0, 0, square root of gamma 0, and we are also going to need L dagger L. Will be just multiplying this by this. First line, first column, 0. First line, second column, 0. First line, 0. Okay, so this is our model. This is now totally defined. So the question here is, I have this model, how I can calculate this rho. Okay, it will be a set of differential equations that you will see that they can be solved at least in theory very easily. Okay, but first of all we have to be able to write down this set of equations. Okay, that is non-trivial from the derivation, or it's trivial if you understand it. So let's do many calculations ahead. Okay, so let's just write this explicitly. The density matrix will be formed by something like this. T, 1 T. On the left we have the derivative. This will be equal to this part. Hamiltonian, 0j, j epsilon, density matrix, rho 0, 0, rho 0, 1, rho 1, 0, rho 1, 1, minus rho 0, 0, rho 0, 1, 1, 0, rho 1, 1. Hamiltonian again, 0j, j epsilon. Okay, all of this is the coherent part. Okay, and now I'm very grateful for having such a big blackboard, because now we have to write the incoherent part as L, that is 0 square. Let's take the square root of gamma out, and there are two of them. This will be gamma, this will be 0, 1, 0, 0, rho 0, 0, rho 0, 1, rho 1, 0, rho 1, 1, dagger 0, 1, 0, 0, minus 1/2 gamma 0, 0, 0, 1, rho 0, 0, rho 0, 1, rho 1, 0, rho 1, 1, minus gamma half again, rho 0, 0, rho 1, 0, rho 1, 1, 0, 0, 0, 1. Okay? If I name them, I don't know if the camera can grasp the whole equation. Okay? Otherwise we just quite a very long equation. And now, very long calculation. because what very easy, but very long, because what we have to do is to start multiplying all these matrices, basically. Okay. So this will be equal. Let me move here. This part. Let's see if I don't make many mistakes. First file, first row, first column, J row 1 0. First row, second column, J row 1 1. Second row, first column, J row 0 0 plus epsilon row 1 0. This and this, J row 0 1 plus epsilon row 1 1. Okay, if something is wrong, you scream and tell me. Okay. If it is wrong, it's your fault, not my fault. Okay. Second one, J row 0 1. The other one, J row 0 0 plus epsilon row 0 1. J row 1 1. J row 1 0 plus epsilon row 1 1. Okay. As here there are two multiplications, let's make one here. This will be, this is very easy. This row 1 0. This is this row 1 1 0 0. Okay. So let's go. Plus gamma, now it's this times this times this, row 1 1, now 0 0 0. Okay, as you see, it's not complicated, it's just tiring. Minus half. This and this, 0 0, row 1 0, row 1 1. Minus gamma 2, 0, row 0 1, 0, row 1 1. Okay? Are we happy? So let's sum. The coherent part will be inside this J row 0 1 minus row 1 0. This will be J row 1 1 minus row 0 0 minus epsilon row 0 1. This minus this, J row 0 0 minus row 1 1 plus epsilon row 1 0. And finally, J row 0 1 minus row 1 0 0. Then there is something wrong. Let me check. No, this is row 1 0 minus row 0 1. This is inverted. Okay. 1 0 0 1, and here is 0 1 1 0 minus epsilon row 1 1. Hopefully. No?
You cancel the epsilon.
Yes. Thank you. This cancels. This here cancels with this here. Okay? Now, incoherent part. Row 1 1 minus row 0 1 half, no, from here, minus row 1 0 half from here, right, minus row 1 1. Okay? And basically that's it. You see, here we have the derivatives. So each of the elements of the density matrix is a function that depends on time. So we have here our 4 functions that we have to solve as a function of the other functions. Okay, so this now we can write as just a set of differential equations. Okay, let's write it here. So basically we get a set of differential equations. Let's see. Rho 0, 0 dot of t. Let's write in order. Here will be rho 0, 0, rho 0, 1, rho 1, 0, rho 1, 1. Okay? So rho 0, 0, how does it depend on rho 0, 0? This, you see, this is the element we are looking, this and this. Okay? From rho 0, 0 it does not depend. So it is j rho 0, 1 with the minus I plus, so, yes, plus I rho 1, 0, if I'm not wrong, because this minus multiplies here, okay, plus gamma rho 1, 1. I think, okay? You have more eyes than I do, so please. See. Now, this element is equal to this part here, so it's I j rho 0, 0 first, this element here, minus, it will be minus I j rho 1, 1, and in the middle, only epsilon rho 0, 1, minus epsilon rho 0, 1. Minus epsilon gamma. Ah, no, sorry, another gamma, yes. And the gamma is, we are looking this, minus gamma rho 0, 1, minus gamma half rho 0, 1. Okay?
I think perhaps in the first equation, the 2 first terms are the opposite sign.
Let's see, it's rho 0, 0, okay? We are ordering them 0, 0, 0, 1, 1, 0, 1, 1, okay? So the first is this one, okay? So the rho 0, 1 is positive because it cancels. That's true. This is positive and this is negative. It's 0, 1 and 1, 0, okay? In the other case, we check. So in the other case, there is also something missing, that is an I here. Okay? Because it comes from this epsilon here. So minus I epsilon.
It should be a plus, no? You're looking at the top right corner.
Oh, yeah, sorry. It's a plus. Yeah. It's a plus I. Okay? You see? It's very easy to get confused. Now we are in this corner, okay? Mark it. Okay, now it will be minus I j rho 0, 0. Now 0, 1 appears. It does not appear. It does not appear. Then, and this is 1, 0, okay?
No, it's
0, 1 will be the plus sign.
This is 0, 1 too, sorry? 0, 1, yes, no, sorry. This is here, so this is minus gamma half plus gamma half rho 1, 0. Okay, 0, 1, 0, 1. Okay, now it makes sense. Because here we are going now to get something regarding rho 1, 0 and not 0, 1. Okay? It makes sense. Rho 1, 0 will be here minus I epsilon minus gamma half. Okay? Hopefully.
I think we made a mistake also on the previous one.
Where?
So in that matrix here, in the previous one, the one over there.
Yeah?
I think that, the diagonals in the second term, they should have negative signs, no?
This and this
Yeah.
should not have negative
No,
sign?
they should both have negative signs. You only have a negative sign on the one at the bottom, but the one at the top should also be a negative.
No, yes, no, it's a negative sign.
Yes.
It is easily written, and this, yeah.
That's the dissipation, no?
Yes, we have to decay. Yeah. Okay. Okay. Now, row 1 of T. The last one. So going to be no 0, 0. For 0, 1, it will be minus ij. 0, 1 plus ij row 1, 0 minus gamma row 1, 1. Okay? So now you see also why it is important to get a way to tell Mathematica to solve this, because it's quite painful to live with all the terms. And this is only 1 qubit. You go for 2 qubits, it's a total mess. Okay? So we have to solve this set of equations, basically. At the end, we have to calculate these functions as a function of time. You see, of course, we get a linear set of equations. Okay? And this connects with the next technique. Of course, I think we get a linear set of equations because quantum mechanics is linear. So usually we get linear equations. Okay? This, if you see, we can write in the following way. Okay? It's just a mathematical thing. Imagine that the row is like this: 0, 1, row 1, 0, row 1, 1, dot, 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 t, t, t. Now I decide to write this as a vector just to summarize this. Okay? This will be equal to a matrix that will be 0, ij minus ij gamma ij I epsilon minus gamma half 0 minus I j minus I j row 0, 1 is 0 this time, minus I epsilon minus gamma half I j 0 minus I j minus gamma multiplied by row 0, 0, row 0, 1, row 1, 0, row 1, 1, t, 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 okay. Okay, so this is the same set of equations written in a different place, okay, different way. And this is what is called to move to the Fock Liouville space. Okay? So basically, we went from the original equation, where we have an equation working on matrices. We have something that is acting on these matrices. That is what usually we call the super operator, because it's an operator on operators. Okay? But there is this trick that can always be used. If I take my matrices and transform them into vectors, then my super operators transform into matrices. Okay? And this is, so basically what we have done is going from one matrix row to one vector row. Okay? And in this case, my super operator, all what the Limblad master equation is doing, is condensed in this matrix. That is what is called usually the Liouville. Okay? So written this way, the Limrat master equation can be formally written as rho dot T equal to our Liouvillean acting on rho. Okay, a Liouvillean that now is a matrix, and we can work with it. Okay. So now it's just, this is going to the Fock-Liouville space. It's just a trick to go to work with matrices. That is something that we are very used to. Okay. So now we are ready to really see how to solve this equation by analyzing the properties of this Liouvillean matrix. Okay. So let's erase from here. Let's start here. Okay. And usually what do we do when we have this kind of linear set of equations? And it is work with the spectral properties of our matrices. Okay, we know now we have our matrix that we have calculated, okay, that you can also make automatic, and we want to solve this equation. Solving this equation as it is written, now it's written this way, rho dot of T is equal to L of rho. The solution is extremely easy to find. I mean, this is very similar to the Schrödinger equation. You know that L is rho of T will be just exponential of LT rho of 0. Okay? This is trivial to solve. It's like the Schrödinger equation, but you lack the imaginary number. Okay? But then the question is, and it's the same in the Schrödinger equation, what does the exponential of a matrix means? Okay? In the Schrödinger equation, if you have taken any simple course in quantum mechanics, you see that it's easy, and it's going to be the same technique here. You can say, okay, I just have to diagonalize the matrix, write everything in this basis, okay, and then I can proceed with it. Okay. The only twist here, the only different thing that makes it numerically more difficult is that if the Hamiltonian is a Hermitian matrix, you can apply the spectral theorem, knowing that if you diagonalize it, you get a set of eigenvectors that form a basis of your system, of your Hilbert space. Okay? The Liouvillean matrix is not Hermitian. You can just see the matrix we have found, and it's clearly not Hermitian. Okay? So it's also not a random matrix. Okay? We will see that it has to fulfill some properties, but it's not easy to diagonalize. And you won't get a set of eigenvectors that form a basis of your system. What you get, and this happens for matrices, so what we can define, it's not correct now to talk about eigenvectors. What is right to say is that we have left eigenvectors and right eigenvectors. Okay, so we can diagonalize it and finding the left eigenvectors meaning something like this, that when you apply the Liouvillean, you get, call them lambda I, here lambda I, the same. So, okay, but you also have right eigenvectors. Such that L, I, let's call them left, right, I, right. Okay, and the promise is that this set, the full set of left and right, they form what is called a bi-orthogonal basis of your Hilbert space. Okay. So it's a little more complicated. I mean, it's for sure much more complicated to diagonalize a general matrix than a Hermitian matrix. Many of the techniques, numerical techniques that are used for regular, for Hermitian matrices, they don't work now. Okay, but at the end you get with something that is not so complicated. So if we want to work with this equation here, we want to solve our Lindblad master equation, what we have to do is to take our density matrix and expand in this bi-orthogonal basis, meaning.
By the way, I think technically we should call it the singular value decomposition.
The
This left and right.
left and right is called, the singular value decomposition, more than the diagonalization.
Yeah, exactly. Because you call the spectrum, that's what I'm saying.
Singular value. It's not called officially spectral because you cannot apply the spectral theory. Okay, it's singular value decomposition. Yeah. Okay. So basically, what we have to do is we find the eigenbasis. Okay. And now that we have this eigenbasis, we take our initial density matrix and expand in this eigenbasis. That should be something like this. Left, row T, row 0, sorry. And that's y. Right. Okay? So this is the expansion of our density matrix that now we write as a vector. Okay? In this bi-orthogonal basis. Okay? This now we can use here. So our row of T, vector form, will be exponential of T times this I and I, row of 0. This is left, and the I, this is right. Okay? This just a constant, this is here, and as these are the eigenvectors of the Liouvillean, what we get is just sum over I of the I, row 0, F, exponential of lambda I T, lambda I. Okay? And you can propagate your initial state to any arbitrary state just by applying this formula. Okay? So what is the computational cost here? Diagonalizing the Liouvillean. Then it is just making a very small number of multiplications here, exponentiations, and then you can calculate. Okay? Of course, for practical purposes, there is another way, that is solving the differential equations. What is better? It depends on the problem. Okay? Usually, diagonalizing very, very big matrices can be very cumbersome, very expensive, or even impossible. Okay? So if you have many qubits, you have a high dimensional system, probably you won't be able to diagonalize the Liouvillean. Even sometimes you are not even, it is not even possible to store your Liouvillean in your computer if you have a normal computer. Okay? So usually I would say that now the limit for normal computing is around 10 qubits, something like that, with a small supercomputer as we have here. 10 qubits, 11 qubits gets very, very difficult. Okay? But if you cannot diagonalize, you can solve. For this, you can make it on the fly, calculating all the equations all the time, so you don't need to calculate the metrics, so you don't need to store it. But on the other hand, it's more time consuming, and you have to do every time. Here, if you diagonalize and you get the eigenbasis, I give you a different initial state and you can calculate immediately, basically, the output. Okay? Also, from the non-spectral, but from the singular value properties of the Liouvillean, we can know some things. Okay? As I said, the Liouvillean is not a Hermitian matrix, but it's also not a random matrix. Okay? Okay, now let me keep it here. Well, I was going to call this spectral properties. Okay, let's say properties of the eigenvalues of lambda i's. Okay. I mean, from this we can easily see that this Liouvillean, even if it is not Hermitian, not diagonal, or not nothing easy to try the diagonal or whatever. It cannot be anything. It cannot give you a random eigenvalue, for instance. Why? Imagine that you have an eigenvalue that is 100, okay? So when you calculate the time evolution, this will be the exponential of 100 times the t, okay? And the t grows, 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 grows. So there will be one of the components of this matrix, one of the components of the density matrix that grows, 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 grows exponentially, okay? And this cannot happen because the trace of the density matrix should be preserved, okay? This is easy, relatively easy to prove, okay? So it can be proved that all real parts of all the eigenvalues should be smaller or equal than 0. Okay, you can have a decay, but you cannot have an exponential growth of any of the eigenvalues. Okay. So if we plot the eigenvalues, they will be like something like that. These are the real parts of the eigenvalues. These are the imaginary parts of the eigenvalues. Okay. So all of them will belong to this part of the axis. Okay. And we can divide them in several kinds. For instance, if we have eigenvalues here, which are very common, what do they represent? Everything comes from this formula, okay? If this is a real negative number, what will happen to this component of the density matrix with the time? If this is exponential of minus 3t, what will happen? When I increase the t, it will exponentially decay, okay? So these are called decay channels, okay? Okay? Imagine that we have, and we can also prove that we have, if we have an eigenvalue with imaginary part, you should have also its complex conjugate as an eigenvalue, okay? This is something that you can also prove. What will happen with this kind of eigenvalues, okay? But this and the other thing, okay? Now we have here this lambda I is a complex number, okay? So if it is a complex number, there will be oscillations, but it also have a real part that is negative, okay? So there will be an oscillation and it will decay, okay? So we will have damp oscillation, okay? These are usually called oscillating coherences. Oscillating coherences. These are decay plus oscillation, okay? And of course, there are many of them, okay? There is another special case. Imagine that we have, in principle, it could happen, and let's go to this case, that I have an eigenvalue that is 0, okay? As I have said, all the eigenvalues are equal or smaller, the real part are equal or smaller than 0, okay? If I have one eigenvalue that is 0, and if I wait for an infinitely long time, what happens?
Nothing happens, it's just a steady state.
Exactly. It's the only one that will survive all these decays, okay? All of them will decay, except this one. It doesn't evolve. So this is the most important point, that is the steady state. And we will talk a little bit more about them, about this, because it's of course the most important case, okay? And there is only another possibility that it doesn't happen very often, sometimes, okay? Oh, we have a very, very small green one. No, too small, okay? White. Could happen that you have also a pair with 0 real part, but non-zero imaginary part, okay? What will happen with these states? They will survive because they have no decay, but this will oscillate forever, okay? And this is what are called oscillating coherences. Okay? So this is basically how the spectrum of a Lindblad-Liouville can look like. Okay? And it's also applicable to other master equations, because most of the arguments we have said, most of the reasoning that we follow here can be applied to other master equations, because you cannot have a positive eigenvalue, otherwise you don't preserve the trace. Okay? And this should happen in any map that is trace preserving. Okay? So cool. So if you diagonalize your Liouville, you get a lot of information. You can propagate it through time, okay? But sometimes you don't even to propagate. You don't need to propagate through time. Why? Because in physics, many times, what we are interested on is in the steady states of things. Other times not. Other times we want to see evolution. But sometimes we want just to know what is the steady state of our system. If we want to know the steady state, this we don't need to do, because we already know what the steady state will be. Steady state corresponds to this element here. Okay? So the eigenvalue that corresponds, the right eigenvalue corresponding to this the right eigenvector corresponding to this eigenvalue, okay, will be this one that will be the only one that survives. Okay? So here, let's go to steady state. Basically, we can claim that if lambda sub I is equal to 0, this implies that lambda sub I, that is lambda sub I, is a steady state. And you can prove that this lambda sub I that you get is a positive matrix, because otherwise it couldn't be the steady state of the system. Okay, usually by diagonalization, so you don't get it to be trace equal to 1, okay, but it is positive. Okay, there are only, in a paper of mine, there are only some very weird counterexamples. Okay, they're coming from symmetries. Okay, but in general, you take a system, you diagonalize, you take the 0 eigenvalue, you take the eigenvector, this is a steady state. Okay? One question that we may ask is there a steady state for every system, for every Liouville that I gave you? And the answer is no, but yes. I mean, there is one theorem, that is Evans' theorem, stating that if your Hilbert space is bounded, then there is at least one steady state. Okay? At least one. There can be more than one. Yes, you can.
Do we know if the eigenvalues are non-degenerate?
The eigenvalues can be degenerate.
Even for the steady state?
Even for the steady state. I will explain now. Okay? So, we know that there is at least one steady state. Okay? The other eigenvalues, they can be degenerated. We don't care so much, usually, because they decay. Okay? But the steady state, can it be degenerated? It can. And I have at least 4 papers on this matter. Okay? The steady state can be degenerated if the system has some inherent symmetry inside of it. Okay? There are 2 kinds of symmetries. One that is called strong symmetry. Meaning that there is an operator, the operator is called O, such that H of O is equal to H of Li, that is equal to 0. So if you, H O, Li O, okay? So, and this is very similar to what happens in closed system. If I give you an operator that commutes with the Hamiltonian and commutes with the jump operator, okay, then the system is degenerated, and you have different. Basically, you can analyze in the eigenbasis of this operator, depending on this operator eigenvalues, it's called lambda 1, lambda 2, lambda 3. You will have different subsections of your Liouvillean. And for each of these subsections, you can apply the Evans theorem, and you will have at least one steady state for each of these subspaces. Okay? This is what is called a strong symmetry, and there is also what is a weak symmetry. Meaning that exists another operator such that commutes with the Liouvillean itself. Okay? And this is harder to study, but it also, you can prove that it leads to multiple steady states. Okay? The question is, all degeneracy in the steady state come from symmetries? We don't know. I have tried to prove it for many years. I couldn't. I guess other people, brightest people, have also tried. Nobody could so far. Very difficult thing, because if I give you a Liouvillean, I prove that it is degenerated. Prove me that there is no symmetry, that there is no such an operator that commutes, or prove me that there should be an operator. It's a complicated task. Okay. If I give you a Liouvillean, tell me how many steady states does it have? Also very hard. Okay. And this was solved by my coworker Yuthar Thingna and myself. If I give you a Liouvillean and it is degenerated, recreate me the steady states is also very difficult. Okay, because in this case, as I say, when you have only 1, 0, then you take the right eigenvector, and this is a steady state. Okay, and if there are 2 of them, then you have 2 right eigenvectors. They should not be necessarily positive, because they can be just the combination, the linear combination of the 2 density matrices. Okay, and if you have many, it is very difficult. So we develop a method just to recreate, starting from one of them, recreate all the other ones, and but it's only applicable if you have 4 or 5. If you have many, but this dimension of your system is very big, then it is very, very difficult. Okay. Okay, so this is the resolution part. If you go to my paper, you can see for the examples we did many examples, and I don't want just to write them down. I don't think it makes sense. They are already written. Just discuss a little bit about the phenomenology. As I say, in this example we have here, what we have is a driving between 2 levels with a decay channel. Okay, so basically, if we plot some of our elements of our density matrix as function of time, let's try to grasp a little bit of the phenomenology. Okay, imagine that I make gamma equal to 0, j different from 0. Okay, and I plot, let's say, rho 0, 0. What will it happen? This is closed system, okay? This is not, because if I make gamma equal to 0, there is no dissipation. It's only closed system.
So you will have an oscillation between 0 and 1, depending on where you start.
It will depend on when you start, but it doesn't matter in the sense that you will have for sure an oscillation. Okay? If it is 0, it will go to 1 and back, and 1 to back, and if it is in 1, the value, okay? And this will be, for instance, rho 0, 0. This will be, start here, rho 1, 1. Okay? These are the populations. These represent the probability of finding the state at 0 or 1. So they are not very difficult to grasp. Make it here. What will happen? The opposite case. J is equal to 0, gamma is different from 0. I have erased the matrix. It's not very easy from the matrix to grasp it. But you can see it a little bit from the form of the jump operator. what does the jump operator? Takes 1 and transform it into 0. Okay, so if you start with 1, for instance, is throw 1, 1 is here, this is 1, throw 1, 1 is here, what you will get is a exponential decay. Okay. And what will happen to row 0, 0? Just by trace preservation, should go like this. Okay. What will happen if we combine them both? Basically, they say this represents somehow our Liouvillean, this represents these points here, that they oscillate and they never decay. Okay, this in our Liouvillean represents something like this. Yeah, exponentially decay. Okay, except this will be row 1, 1, and row 0, 0 will be here because it's the steady state, because it just decays and remains there. Okay, what happens if we have gamma different from 0 and j different from 0? For if we start at 1, we'll oscillate, but it will also decay. So basically it's the combination of these two. So 1, 1 was this one. Something like this. Okay? Because in this case, if you see the spectrum, this corresponds to something like here. Okay? This will be somehow. Okay?
Is there a relationship between the magnitudes of gamma and j, so you can have, say, overdamping, underdamping?
Yes, this could be if gamma is much higher than j.
So
it could happen also, of course, something like this, that you don't go to 0.
And then there's the critical damping where you only have
Okay. And if j is much bigger than gamma, you will see again oscillation. Okay. Because of course, if you are always coherently populate the level 1, you don't go to 0 really. You will go to something that is between 0 and 1. Okay. So this will be gamma very big, and this is gamma not so big. Okay. And this, of course, this is a very simple example. You can go in my paper, this paper that is written there. We can include also in the comments of the video. You can see the examples, and you can download some mathematical notebooks to play around. Okay, but if you go to many qubits, it's very difficult. It's very difficult to have an intuition of what is going on. This is why many people, we work in the Limblad master equation, and we do things, and we don't know what is going to come out. Okay, because it is a very complicated master equation. Okay, so I think this is everything. So I hope that you can now deal with any master equation that you find. Okay, and then any more questions? Okay, thanks for your attention.